This course may seem like it has an awful lot of pieces, and it does, but as we've mentioned before, there are an awful lot of things you need to learn before you can actually be the consummate programmer. One of these is a knowledge of numbering systems, and particularly binary. It's a little less painful if you learn this in small steps, so we introduce binary in this course. When you take the next course, the CIST 1400, chances are you might have to write a program that deals with one of the other numbering schemes, either binary or octal, which is base 8, binary is base 2. So to get a little bit of a look at it here is a little less painful than trying to assimilate the knowledge while you're learning to do the logic for a different program. There are many types of numbers and sizes, and every time they come up with a different processor, these change a little bit, a lot. So, caveat, I'm not sure if all of these numbers are correct. I did a little looking and couldn't find specifics. But the byte has 8 bits, or binary digits. These digits are either on with electricity flowing through them, or off, electricity not. So that's why it's called binary. There are 2 states, electricity, no electricity. The byte is capable of doing numbers 0 through 255. Then we have short integer, which is 16 bits. It's negative 32,000 through positive 32,000. Integer is 32 bits. See, it used to be 16, but now it's 32 because of the bigger processors. It's a negative 2 billion something through a positive 2 billion something. Long integer is 64 bits. It's got 6 sets of 3 numbers, if you do a comma in between each one. And so it's 9 times 10 raised to the 18th power. That's really big. As far as I know, single allows you to have 38 digits, but the significance and the difference is you can have decimal places with the single type of number. Double, 308 digits, also with decimal positions. And currency is 19 digits and up to 4 decimal places. I could not find this written about in your book, so I'm assuming that's correct, but it might have changed. How do number systems work? This is some principles of how in the world our whole math system works. You need to understand these before you can convert to a different numbering system. Let's take the number 2,435. I think you would agree that it's composed of 2,000, which is 2 times 1,000, which is 2 times 10 cubed, or 10 to the raised to the 3rd power. It's also 400, which is 4 times 100, which is 4 times 10 squared. And then it's 30, which is 3 times 10 to the 1st. And finally, the number 5 is 5 times 10 to the 0th. Take a look at those powers of 10 in the far right column. Notice how it's 3210. 10 to the 0th had to be mathematically equal to 1 for this whole system to work. Again, take a look at these. Make sure you understand how this came about, or how this works. Got a question for you. What happens when you add 1 to the number 9 when we're in base 10? What answer do you get? Did you say 10? Bzzz. Nope, it's not 10. Let's do some basic principles here. The digits in base 10 are not 1 through 10. They are 0 through 9. So that means the highest digit is 9. And I asked you, what happens when you add 1 to that digit? And you said, well, you get 10. No, it's not 10. Yeah, I know it's a technicality. But when you add 1 to the highest digit, the answer is 0 carry 1. That's a really important concept. The person who invented this is the original mathematical genius, because then we were able to increase the number of places and come up with the whole base 10 numbering scheme. Oh, the number 11 is not some symbol. It's start over when I get to 10 with a 1 in the second position there. Let's compare base 10 and base 2. In base 10, the digits are 0 through 9. Notice the digits are not 1 through 10, 0 through 9. In base 2, the digits are 0 through 1. 1 is the highest digit. Back in base 10, if I add 1 to the highest digit, 9, it's 0, carry 1, or 1, 0. In base 2, the highest digit is 1, and so when I add 1 to it, it is also 0, carry 1. Okay, let's go take a look at a number in base 2. We'll just do a whole bunch of 1s, remembering that our only two digits are 0 and 1. I'm sure you'll agree that that's 1000 plus 100 plus 10 plus 1. That those numbers would make up the bigger number. Let's use the previous principles and figure out what this number is. The first one is to the third power. So it's 1 times 2 cubed because we are in base 2. As before we were in base 10 and it was 10 cubed. So here it's 2 cubed. And the next one is 2 squared. The third one is 2 to the first. And the fourth one is 2 to the 0th. Remember, 2 to the 0th would have to be equal to a 1. So again, in the second column, notice the exponents 3210 follows the same idea as base 10. And then if you carry it out, we can see what each one of these is worth as a placeholder. You add them up. 1111 in base 2 is 15 in base 10. 1111 doesn't have very much meaning to most people. So we need to convert it to make sense of what the computer's doing. In fact, if we look at these values of the placeholders in a binary number, starting at the far right, 2 to the 0th is 1. 2 to the first is 2. I'm working toward the left. 2 squared is 4. 2 cubed is 8. 2 to the 4th is 16. 2 to the 5th is 32. 2 to the 6th is 64. And 2 to the 7th is 128. If we were to continue on going to the left, it would be 256, 512, 1024, 2048, 4096, 8192, and I can't do it any further than that in my head. Let's figure out what this particular binary number is. So if I have my different place values up there to prompt me, I see that it is 32 plus 4 plus 2 plus 1, which is 39. Now, some of the mistakes folks make when they do the problems here could easily be solved, well, or at least they would get a clue that they were wrong. Somebody might say that this one is 38 or 40. You should ask yourself a question. Is this binary number that I see even or odd? Here's the rules. If the number ends in a 1, it's an odd number. Has to be, because 2 to the 0th is 1, which would be the rightmost position. If it ends in a 0, they are even. So let's stop right here. When we'll come back, we'll do some math in binary.